Good time of day, ladies and gentlemen. My name is Jar and I represent the team Soloplay. Previously, we discussed and presented the energy demand forecasting, and here we pitch our own approach to trading wind energy. So without further ado, let's begin our presentation. There are two datasets of wind forecasting and wind energy upon which we will build our forecast and trading model, and they mostly represent seasonal data from the beginning of 2017 to this particular moment. Now, regarding the extraction of data for sampling, training, and testing our neural net, we got 5 separate tables of energy indicators combined into one and elucidated into the columns to the following figures. In other words, there was not interpolation but a fusion of data. As for the time series, we tried to define the seasonality and deduce some possible trends in the data. For that purpose, we attempted to decompose additively and multiplicatively. Unfortunately, multiplicative decomposition resulted in failure, and we decided to proceed with former one. From the graphs that you see on this slide, it can be said that we tried to decompose by 18 hours, monthly, and yearly. However, as a result, the first two showed us noisy and unclear data, furthermore, no trend. Nonetheless, yearly one shows obvious seasonality due to the general and broad extent of gathered data. When it comes to feature engineering, to existing from previous labs min, max, standard deviation, and mean values, we added skewness for checking any asymmetry in our future real-world data distribution. On this slide, as you can see, we ran our initial naive model and got quite unfortunate results in terms of vast difference between test and train losses, test being the highest, and huge loss indicators. This is because we didn't try to add new features to make the raw data cleaner and train properly our network, but used different features utilized in the previous lab. Scatter plots and prediction graphs clearly illustrate the diversion and dispersion of data across the axes, and not generalized model in terms of spike of test loss and multiple peaks on the lag correlation diagram. By adding bottleneck size as 2, momentum and force features, and setting clump on scale value as true, the model significantly improved. The persistence that we got initially as 0.445 was clearly beaten by our network, and its minimum loss reached 0.32885. The pattern of very close approximation to gradient line in both training and test predictions and lag correlations, reduced number of peaks, and general trend of decreasing of losses, lag equal to 0, makes the learning of neural networks undoubted and certain. Finally, according to the results of Lab 6, the net profit of our sales is 1.5 billion euro cents. It's what we got after a small technical update from our instructors in the back end of our software on which we were training our model, because before that we got 600 million euro cents. Therefore, we can safely say that this change in our network's ability to learn on its own led to more effective and efficient results in terms of final profit of trades. While the results are great, we can always find the room for improvement. There may be a potential to make results even better with implementation of trigonometric approximation, averaging all results, and interpolation and use of kurtosis to find general patterns in our network's learning curve. That will be all, and thank you for your attention.